let's take a look at F1. So F1 is connected to the F0 through this gamma subunit that we've already mentioned. And F1 largely is the alpha 3 beta 3 subunits that make this 100 angstrom by 100 angstrom sphere. So this is a very large protein complex, folks. As a quick note, only the beta subunits catalyze the ATP synthesis. The alpha subunits are more structural in nature. The alpha 3 beta 3 subunits have 3 different conformational shapes. We have the loose, or L, that binds substrate, the tight, or T, that is catalytic, and the open, or O, that releases substrate. So in a top-down view, then, of the alpha 3 beta 3 subunits, we could kind of divide this into 3 sections, each with 1 alpha and 1 beta subunit. Now the movement, let me erase this ink real quick. Now the movement that we saw of that C ring rotating around is translated through the gamma subunit, right? So when C rotates, gamma rotates. However, the alpha 3 beta 3 subunits do not rotate because we have this other protein subunit, folks, that's kind of holding on to them. So up here at the top, we are not rotating, even though gamma in the middle here is rotating within the alpha 3 beta 3. So this top-down view, then, we can understand would look something like one dimer of alpha and beta being in the loose, 1 dimer of the alpha and beta being in the tight, and 1 dimer of the alpha and beta being in the open. Now when the gamma rotates, that's going to cause the conformational changes so that each of our dimers are in a new conformation. So alpha 1, beta 1, once gamma rotates, would then be in the open state. And the alpha 2, beta 2 would then be in loose. And alpha 3, beta 3 would then be in tight. So you can see how by gamma rotating caused this kind of shift of conformations in each of the alpha beta dimers. Now that is challenging to explain with words, so why don't we watch this video to understand in 3 dimensions how this can happen. So here, folks, before I press play, this video is showing us a 3-dimensional view of the ATP synthase. Down below here, we're going to have the C ring and the A subunit connected through this vertical subunit here, which is going to contain the gamma subunit, and this ring up top, the alpha 3 beta 3. Now as that gamma subunit rotates, you can see how these pink subunits change shapes. If we zoom into the structure, we can see how those shape changes allow substrate in and out, with reactions happening along the way, so loose, tight, open. In the loose state, we bind our substrate ADP. How is ADP being bound? Well, there's a variety of R groups coming from the alpha 1 beta 1 subunit, performing nice hydrogen bonding interactions with our substrate. Of course, ATP is a nucleotide, so we need magnesium for charge stability, folks. In addition to ADP being one of the substrates, we know that we need a phosphate as well. In comes phosphate, and a conformational change to the tight state allows the chemistry to happen, and bam, there is our ATP that has been synthesized. Now into the open state, the substrate is released, back to the loose, tight, open. Loose, tight, open, right? And so these conformational changes, the physical shape changes, are leading to the catalysis that we just saw. Let's zoom back out for a second. There's the gamma subunit rotating, and it's rotating because of what's happening at the C ring and the A subunit. Let's take a look at that as well, because it'll be a little bit better than my drawings. Here we see the C ring. These balls that are getting sucked in are the protons. You can see the big difference in the concentration gradient, right? The inner membrane space, super acidic with all those protons. The matrix, super basic, lacks protons. Those protons come in through the access channel and are grabbed up by that aspartate because of the difference between the pKa and the pH. As those aspartates rotate through, the protons are eventually released into the matrix again because of the difference of pH and pKa. I'm going to pause the video real quick here because it was moving just a little bit too fast for me. But what you could see there is, in addition to the protons being sucked in and released, you can imagine that right here in between these two yellow circles is our arginine, where that negatively charged aspartate is being pulled towards that arginine as we grab and release those protons. Now here, what we're looking at, lastly I want to show you this, is we're visualizing how this gamma subunit rotating kind of pushes the alpha 3 beta subunits. That physical push is what's causing those shape changes to allow the loose, the tight, the open state. I thought that video was very helpful. Last up, folks, we'll talk about some final ideas about electron transport and ATP synthesis.